Hello everybody. Today I'm going to speak about the analysis that we have done at the Barcelona Supercomputing Centre on the CMIP 6 overshoot scenarios. We will see during the presentation that in case of overshoot, if the global temperature is recovered after the overshoot, there are some irreversibility mechanisms that are put in place and that makes the situation after the overshoot different from the situation of before, in particular in terms of ocean heat transport, in terms of sea ice, and all these changes impact also temperature and precipitation, especially in regional scales. So in the CMIP 6, we have two overshoot scenarios, the 534 with larger forcing changes and the 119. And if we analyze directly the global temperature, we see that indeed the global temperature after the overshoot is the same as before. It is recovered. But, for example, it is different if we only consider the land areas. So there is clearly some regional changes. One thing that we see here is that even if it is recovered, it may take a long time. For example, in the case of the 534, we see that the full stabilization is not reached before 2200, for example. This is a limitation because if we analyze the simulation for the CMIP 6, we see that most of the simulation stop at 2100. So the situation is not fully recovered for this simulation. There were only 4 simulations covering up to 2300. Here we speak about extended ensemble. And for this, we are able to analyze the situation after the overshoot. During the overshoot, we see that indeed, we know that for the warming phase, there are differences depending on the region. We see the typical pattern in which the continents and the polar areas are increase the temperature more than the ocean areas. But it is the same for the cooling phase. In the cooling phase, we have also differences depending on the region. In particular, we see that for the cooling, we have, for example, after the maximum, that most areas in the northern hemisphere have already started to cool, but most areas in the southern ocean, for example, continue to increase the temperature. If we check, for example, the year of the temperature maximum, which is the figures in the middle of the slide, we see that the maximum is reached before for continental areas, especially for the northern hemisphere, and the maximum is delayed for the southern ocean. And we can see very clear that the same temperature as before the overshoot is only recovered for the northern hemisphere, not for the southern hemisphere. So it is clear that there are changes that are irreversible, that something has happened during the overshoot that makes that the situation after it is not the same as the situation as before. And we see the same for the two experiments, for the 534 and also for the 119. If we analyze this post-overshoot situation, in this case, for the experiment 534, for the 4 simulations that are covered in the extended period up to 2300, we see that the situation is characterized by temperature asymmetries. We see clearly a temperature asymmetry between the north, which will be cooler, and the south, which will be warmer. Of course, if we have this temperature asymmetry, we have changes in the intertropical convergence zone. The intertropical convergence zone shifts to the south, making more precipitation in areas south of the ITCZ and less precipitation in areas north of the ITCZ. Independently on the season, we have the same behavior. These changes may be explained by a larger inertia of the ocean during the warming phase. It takes longer to warm, so it continues to warming even after the global temperature maximum. But there are other mechanisms. We will see. If we analyze the other experiment, the 119, we see that this behavior of temperature asymmetry between north and south is still there, but it is not so clear. And there are other changes. In particular, we see that there is an asymmetry between polar areas, which are warmer, and extratropical areas, which are typically cooler after the overshoot. We have still some shifts of the intertropical convergence zone, but they are not so evident as in the other experiment. Indeed, these differences between experiments are not necessarily linked to the forcing specification of the experiment, but mostly to the models that are contributing to it. We have more models contributing to the 119, so we have a different combination of the models. In any case, these changes with asymmetry between polar areas and extratropical areas may be explained also by changes in the sea ice. We know that there is irreversibility in the sea ice. The sea ice is reduced, the concentration of sea ice is reduced during the warming phase, and it is not fully recovered during the cooling phase. All these changes in temperature and precipitation imply also changes in temperature and precipitation extremes, which may be more important at regional level. We have analyzed also these changes in extreme, and we have found that indeed we will have more cool extremes in the northern hemisphere, in particular in extratropical areas of the northern hemisphere, and more warm extremes in the extratropical areas of the southern hemisphere. If we analyze the link between the regional extremes and the global temperature in the figures in the right part of the slide, we see that indeed there is a coupling between them during the warming phase, with a certain slope depending on the region, of course. During the maximum, both are decoupled. There is no link between the global temperature and the regional maximum. And after the maximum, during the cooling phase, there is a coupling again, but at a different level. In the case of the northern hemisphere, it is a lower level. In the case of the southern hemisphere, it is an upper level. So we are indeed recovering the couple during the cooling phase, but at a different level according to what has happened around the maximum. The same is observed in the 119, but for this asymmetry between high latitudes and medium latitudes. We have also an impact on the extreme. We will have more warm extremes in the polar areas and more cool extremes in the mid latitudes. If we analyze the precipitation extremes, we see that the changes in the intertropical convergence zone are also impacting the precipitation extremes. We have much more precipitation extremes in the areas south of the intertropical convergence zone after the overshoot. And if we analyze also the link between the precipitation extreme and the global temperature, we see also more or less the same behavior as for the temperature. We see that there is a link during the warming phase. If we have more global temperature, we have more precipitation extremes, but around the maximum, that is decoupled. And for the case of the north of the intertropical convergence zone, there is a reduction of the precipitation extremes. And for the case of the south of the intertropical convergence zone, there is an increase. So we have said that the inertia of the ocean may explain part of these changes. We have that the maximum of temperature for the Southern Ocean is delayed with respect to the continental areas, but there are also other mechanisms. In particular, if we analyze the behavior of the ocean after the overshoot compared with the situation before the overshoot, we see that it is characterized by less heat transport in the Atlantic, less mass transport in the Atlantic, which are the top and middle figures in the slide, which means indeed a weaker AMOC. So the AMOC is weakened during the warming phase, and it is not fully recovered during the cooling phase. And if we analyze the sea ice, we see also that there is, after the overshoot, less sea ice than before. So the sea ice is partially lost during the warming phase, and it is not fully recovered. These changes are more or less consistent for all the models, but the contribution of each mechanism is strongly different. There are some models that simulate larger changes in the AMOC. There are others that simulate larger changes in the sea ice. And there is a link between the, for example, between the ocean heat transport simulated by the model and the temperature asymmetry. For those models simulating larger changes in the ocean heat transport, a stronger weakening of the AMOC, we see that there is more asymmetry between northern hemisphere and southern hemisphere temperatures. That makes sense, but what we can see is that it depends on the model. For some models, the changes are small. For others, the changes are larger. And the same for the CIs. We see that for certain models, the changes in the CIs are strong, and in those cases, we see a large asymmetry between high latitudes and medium latitudes of the northern hemisphere. For other models, the changes are not so strong, and we see smaller asymmetries in temperatures. This is more or less the same in the two experiments in this. In the 534, in the right part, in the left part, and the 119 in the right part of the slide. So to summarize, after the overshoot, we see that the climate stabilized to a situation that is different from that of before. In particular, we see that there is an asymmetry between the Southern Ocean and the continental areas of the Northern Hemisphere. There is also an asymmetry between mid and high latitudes of the Northern Hemisphere. Typically, the higher latitudes are warmer after the overshoot, and the mid latitudes are cooler after the overshoot. And we see that all these changes in temperatures imply a change in the intertropical convergence zone, in particular a southern shift. These changes have an impact on regional extremes, with more cold extremes in the extratropical areas of the Northern Hemisphere, more warm extremes in the polar areas and in the extratropical areas of the Southern Hemisphere, and in general, more precipitation extremes in tropical regions south of the intertropical convergence zone, because of this shift to the south. These changes are impacted by different irreversibility mechanisms, including changes in the AMOC or changes in the CIs, but the contribution of each mechanism depends on the model. Different models simulate different relative contribution of one mechanism or the other. If you're interested in these topics, just to say that most of the presentation is included in a publication that was published last month in Earth System Dynamics, and we are currently preparing another one to focus more on these changes in the ocean circulation and the CIs. So thank you very much for your attention, and if you have any question.
Great, thank you so much. If anyone has any questions, feel free to either pop them in the chat or put your hand up. We'll start with a question in the chat from Paul, who says, in slide 8, where the ITCZ shifts south, it looks like the West African monsoon becomes much weaker.
Yep. Yes, indeed. The shift of the intertropical convergence zone has an impact on the monsoon system. Yes.
I am sorry because I'm blind. Can I ask a question?
Yes, please.
It's a very naive question. I want to know what about the interaction between the ice sheets and the climate between the overshoot. Is the ice sheet still prescribed? That means there is no change in sea level, no fresh water added, or is it interactive?
Well, indeed, for the for the ice sheets, this is something that we have not analyzed because it is not necessarily included in all the models. So I think it is something that, from a modeling point of view, the experiment that we have do not really allow us to analyze this interaction. That is the answer.
But you agree that you say that, and you're right. The ocean implies a certain inertia in the system. I believe the ice sheets, just due to the fresh water and also the sea level changes, is also an important parameter. Maybe I'm wrong. I just want to know if there is at least one model that did it.
Honestly, I don't know if some models are taking into account that or not. But yes, you are right. It is indeed important.
Thank you.
Not seeing any hands at the moment. If you think of anything, feel free to put it in the chat, and it can be answered during the next presentation. So thank you so much to Pedro for that great presentation